Hey guys, so today we're going to talk about how you can build your own semantic search engine. We'll talk about like what that even means, but essentially, as a summary, it's more of a conceptual search than just like looking for phrases in text documents that you might find. A lot of you might be familiar with Elasticsearch or Solr. That's usually what they do. They try to find like tokens of phrases inside of the documents for what you're looking for, but conceptual search is a little bit more than that, and we'll jump into that. Before we do, to give you more context of why we were even solving this problem, why you would even listen to me, first let's talk about what Mattermark does. So I head up the data engineering team at Mattermark. I've been there for over 2 years now. By data engineering, really most of what we do is a lot of machine learning, and a lot of that is in the text domain, so a lot of NLP. So why do we even need to do NLP? So what Mattermark does is it tracks and organizes information about businesses. We kind of collect information about 1.3 million businesses, information like what people work there, what industries they're in, how many visitors they're getting on their websites, what their mobile traction is, what kind of social media interactions are being put out for them, what news is coming out about them, and how many employees do they have over time, things like that. So, to get all that data, not a lot of that is like available in structured form on the internet. If it were, then we wouldn't even be creating Mattermark, right? Otherwise, there wouldn't be a business proposition. But so a lot of what we do for NLP is we extract these kinds of structured information from unstructured things like websites, news articles, so on. Actually, if any of you attended my colleague Evion's talk, he talks a little bit about how we do like one of our information extraction pipelines. We also create proprietary data, so predicting what companies. What industries companies are in, like knowing that Mattermark is in the finance industry or Galvanize is in the education industry. Figuring that out, there's no kind of taxonomy out there telling us like what these 1.3 million businesses have in categories. So we have to create that ourselves. We also have features like figuring out what companies are similar to each other automatically. So a lot of unsupervised and supervised machine learning there. And what we're going to be talking about today, search. So how do you find what company you're looking for? A lot of that could be structured search. Like, for example, this one is, show me all the companies ranked by growth score. This is our own proprietary metric for how fast a company is growing. That is in the, I don't know if you guys can see the query, but on the top level, we're looking for Bay Area companies that have at least 10 employees and fewer than 200. So that's a kind of search, right? It's like filtered search. But there's also textual search, and that's what we're going to be talking about today. I think combining these two things has made Mattermark a really powerful platform for salespeople, VCs, and the search, improvement in search is a huge part of that. So let's talk about what traditional search appliances are. So a lot of what you're probably familiar with are, databases that do their own search, like Postgres provides its own full text search. It's a very rudimentary version of search that can find tokens within text bodies that you're putting in your database. There's more intelligent ones like Lucene-based indexers like Apache Solr and Elasticsearch that can take documents and then index it for you and then really quickly serve back results based on the phrase that you're searching for. There's also managed products like AWS Cloud Search, which actually in the back end is either Solr or Elasticsearch. And then there's Algolia, which is a company that handles all of this for you and you don't have to do any of the kind of ops level work. So wait, you might ask, if there's so many products out there, why would you want to build your own? Well, at first, we didn't. We use Elasticsearch, and we still do, but we'll get into how we use it now in a little bit. So we use Elasticsearch to do autocomplete, right? So all of you are familiar with, like, let's say I have 1.3 million companies and I'm looking, I know which one I'm looking for, so I start typing in MATTER. I should get a list of companies that are, start with Matter, so that I can find Mattermark really quickly. So autocomplete, we use Elasticsearch for that. We use it for full text search. So by text, we scrape a lot of information about companies. We use machine learning to figure out what news articles are about what companies. So we have like all the scrapes from the company's website, the company's about page. We have information from their Twitter account of like how they describe themselves, all that stuff. So we have a lot of text from both the company's own information, but also like news articles about how companies are being talked about in the media. So, Elasticsearch is also really powerful, as I was showing you, to do filtering on non-text attributes that are like industries, number of employees, location, all that stuff. So it seemed like it was a really good choice early on. So, and it worked really well. So other than the pain of, I don't know if any of you have used Elasticsearch before, but it's a pain ops-wise. Other than that, customers were really excited to be able to perform full text search on companies. And the fast autocomplete was really great too. So, why would we even build our own semantic search? So really in the end, results were okay. Like after the initial hype that when we put this out to our customers, the initial hype was, oh, this is so great. Now I can search for terms like sharing economy or the new buzzwords like home automation or something like that, and a list of companies would show up. Turns out that the list wasn't very good. It was better than not having a list, so they were excited at first, but later on we realized that it's not really serving the need that the customers have. So Elasticsearch, Solr, Lucene, all of these indexers use a pretty basic NLP technique to figure out what should be shown, and it's based on matching algorithms on BM25 and TF-IDF. So these are very token level matching systems, right? If this is great for looking for like an exact phrase, so if Uber mentioned sharing economy on their website, then it would be a great way to match that. But that's not always the case because people are looking for concepts. So Uber doesn't say ride sharing or sharing economy on its description or its Twitter. So when you search for that, you're not going to have it come up. So the customers aren't really getting what they need because they're doing a conceptual thing. Like in Google, you can get results for web pages even without exact phrase matches because Google is giving you a conceptual search result. So now having that problem, what do? We have a strong NLP team, so we decided, wait, we could easily build our own search. So what we needed was semantic search. So obviously I'm not going to read this. It's Wikipedia. Probably should have prepped a little bit better with my presentation slides, but I'm going to leave that up there. So what does semantic search mean? It's essentially like, can I search for a concept rather than a phrase? So in this case, I want to search for companies that match a given concept. So like chip manufacturers or cognitive training or sharing economy or things like that. People will be looking for a concept that matches a company that a company might not necessarily mention themselves, at least not in the exact words that the customer might be looking for. So what did Mattermark do? So before I get into how we built it, why don't we do a quick demo of what we ended up building and how it compares to Elasticsearch. So I'm going to go quickly over. So on the left side, I don't know, how much can you guys see there? Should I be zooming in a little bit more? Yeah? Let's see. It's a little bit more zoomed in. Yeah, that kind of breaks the sight, but who cares? Yeah, so right now I have, just like I mentioned, I have chip manufacturers as a search on the left side, which is our old system, and then on the right side, it's the new one with the machine learning kind of back end. So obviously, At least, okay, maybe it's not obvious, but I think the right side is better, right? Wouldn't you agree? Anyone else want to try? Anyone want to try any different searches to test me out? See if this is, I don't know, worth even doing? Sure.
You were talking about ride sharing.
Right. Why don't we give that a shot? So I'm going to do, this is the old one. Is my internet not connected? I got logged out. Sorry, guys. Okay, so the right one is already there. Okay, so actually on the left one, it's not terrible. It definitely got some of the stuff. Probably Lyft mentions ride sharing on its site, but Uber doesn't, Ola doesn't, GrabTaxi doesn't, all these things, right? So on the right side, we have a lot more results. We've got 76 there and 22 on the left side. Let's try some crazier stuff. I don't know.
Like this was the right hyphen sharing.
Ooh, I don't know if that's gonna work. That's scary, man. Ooh, Facebook? You broke my system, man. But at least it got some of the right stuff. Yes, let's try breaking the system. And let's try crazier searches. Sorry, go ahead. Traffic cake. What is that even supposed to bring up? All right. Sure. No result there. I don't know what this is. All right.
How do you deal with named entity recognition?
Well, it's just kind of like cakes. So I guess it kind of got confused and said,
well,
you probably don't want traffic cake, you just want cake. But yeah, this is, obviously no one mentions traffic cake, but I guess it works sort of. Go ahead.
How about employee morale?
Ooh, I like that. Okay, so some companies, I guess. Ooh, is Bamboo HR related to employee morale? Maybe. I think these companies. No. On the right side is the conceptual search. And I think the top three are related to employee morale. And on the left side is just stuff that I don't even know if these are actual companies. Cool. Anyone else? We can move on if.
Typos.
Huh?
Data science and mistype one letter.
Missed typos. Ooh. Which one? I don't know if that's going to work. That's definitely not going to work, but I don't know about this one. Well, I don't even know what these companies are. Something. Yeah. I think let's make sure that the actual one works. Okay, cool. All right. Awesome. Nothing else? We can actually get into how this works. Cool. So hopefully you guys think this is actually worth doing. So what did we actually do? Well, one of the problems that we have that Google or Bing or actual search companies that aren't a tiny startup have is a lot of data. They have a lot of click-through data. Did you have a question? No. Sorry, okay. So we definitely don't have enough click-through data. We're a small B2B company that serves about 1,000 users a day. So we don't have anywhere near enough searches to say we can do this with a statistical significance. So we really couldn't create a supervised machine learning-based ranking method. Well, tough luck. So what do we do now? Obviously, the hot take of the last few years has been, can we do unsupervised representation learning? Obviously, deep learning, or other kinds of things. But one of the ideas we had was to project both companies and short phrase queries into a single vector space. So if we could project them into the same vector space, then we could use a distance measure to say what is relevance. and then show the results that are above a threshold of relevance. Obviously, a lot goes into figure out what the distance measure should be. A lot goes into figuring out what the threshold should be. We're going to talk about what vector space we're even mapping these things into. One of the things people who are familiar with NLP and topic modeling might say is that, well, isn't this a solved problem? Couldn't you just use like LSA and LDA to do topic modeling on your company documents? So I expected it. Obviously, I'm going to try it, but I expected LDA and LSA to perform poorly, mostly because they tend to have biases for the length of the document that you're vectorizing. So it's great for comparing similarities between similar sized documents, but when you have something like search queries, where what you're comparing similarity to is a short query phrase and a very large text document, it tends to not be as accurate when you're comparing between other documents. So even though I thought that, I still added it as like a baseline comparison, right? Obviously, I'm also using like the base Elasticsearch implementation as a baseline too. So then we went through, if any of you are familiar with what we do at Mattermark, we've done a lot with Word2Vec and combining it with TF-IDF, so we definitely wanted to try that as a way to generate document vectors and query vectors. We used paragraph vectors, another extension on top of word vectors that kind of tries to encode large text documents into a vector. It's also very good at encoding short documents into vectors. So in my mind, that seemed promising. There was a great paper by, I forget the name, Brian Quiros, I think, about skip thought vectors, and in which he talks about how he could use LSTMs, long short-term memory networks, or convolution neural networks to encode larger bodies of text. The way it would work is it's basically, can you train, so if people are familiar with word embeddings, it's kind of, how do we train sentence embeddings that with recurrent neural networks or convolution neural networks that tries to take the previous sentences in a document and predict the next sentence. So that kind of neural network. So if you want to learn more about that approach, it's a little newer than some of the other ones. I have a link to the PDF. Otherwise, come up to me. I can tell you a little bit about that. So, okay, we're gonna try all these approaches, but how do we know which one's better? So this involves, even though we don't have a lot of click-through data, we wanted to figure out what would give us the best results for the things that most people are searching. So at Mattermark, we have a dedicated data analyst team that helps us with a lot of these kinds of things. So we identified what are the most commonly searched phrases, so things like home automation, ad tech, sharing economy, fantasy sports, a bunch of other things, and we ran experiments on that. So we did like multiple iterations with our data team, like generating results, having them tag like, is this relevant to the thing that people are searching? And we collected that data, and that's how we compared all these different approaches. That's also how we decided on what threshold we should be using, right? This is the kind of approach, it's an approach that's worked really well for us, like an approach that works with an internal data team who are sort of experts on these topics, right? And generating data from nothing, sort of. If you have any questions about that, I can answer that later too. So after doing all these experiments, we landed on paragraph vectors. So the results from the LSTM's convolutional neural network models were actually very similar to paragraph vectors. The actual like precision and recall of those approaches. However, paragraph vectors were far faster to calculate on arbitrary inputs, like when search queries were coming in, we need to calculate the vector right away and return the results. On traditional hardware, we needed to be able to run this stuff in the cloud, in AWS, inside of our regular software stack. So we needed stuff that would, AWS has GPU machines, but they're expensive and not really as good as something you could run on your own computer. So we needed models that would still be able to run well on CPUs. So what we ended up doing was we used cosine similarities for the documents and query vectors and returned the ones above a certain threshold. And the threshold was calculated from all these experimenting to figure out what's the best like precision recall cutoff we want. So let's talk about all the other stuff, because even though we decided on a model, it actually wasn't quite the most difficult thing in our system. So we needed to integrate our powerful ML-based search model into our current ES-based infrastructure, because we had all these faceted search queries, like being able to search about industries or location or how many employees a company had. We needed to be able to do that powerful querying alongside the search queries. So you should be able to say, can I see the sharing economy companies that have more than 100 employees? So to do that, we're already heavily invested in the Elasticsearch methodologies. So we really needed to back into integrating those two things together. We also needed to ensure that we can process hundreds of search queries in a second, because that's probably the max we're getting today. We should also be able to scale out. Like, we should be able to throw in more machines and it should scale. That turned out to not really be the issue. The issue turned out to be, well, how do we actually integrate with Elasticsearch? We looked at a number of different approaches. We could have built our own Java module. I'll explain in a second what this graph is about. We could have implemented our own Java module that plugged into Elasticsearch, but it's a lot harder than you would expect. One of the things that I noticed was that Solr and Lucene actually makes it way easier than Elasticsearch to create your own like custom scoring functions than Elasticsearch does. So keep that in mind if you are ever trying to do this again. Maybe use Solr instead of Elasticsearch. So what we did was we fronted Elasticsearch with a proxy that would figure out if something is a full text related search and then do some proxying. Before we get into that, we also built an ML search service, basically the thing that we just talked about. Well, it's a model, but how does it respond to real-time input from customers, right? To do that, we fronted it with a simple REST API that would accept short phrase search queries, and then it would keep, well, not then, it keeps a paragraph vector model in memory, and also keeps the pre-computed company vectors in memory. Every once in a while, it will do a batch recomputation of those company vectors when information about companies change. So we'll do that like once a month. We will recompute the vectors for these companies and restart all these services. So it keeps that in memory in startup. It turns out to be like 8 to 12 gigs of memory, which isn't that bad for modern servers. So as queries come in, it computes the vector for the query, then does a cosine similarity against all the documents in our company vector space, and then returns the matching document IDs for things that are above the threshold we wanted. So that's like part of it. It'll return like document IDs. But to make this integrated into Elasticsearch, like I said, we needed to have this HTTP app that would act like Elasticsearch. Anyone who is querying Elasticsearch wouldn't need to know that there was some fancy magic going on in the back. It just needs to know, oh, I want to query some text. So it would look the same to everyone. The results are just better. I want to put a plugin here. We use Clojure. First time we got Clojure into a production stack, I'm a huge fan of Clojure, and it was the right choice because it had really, really good stability and throughput. Anyway, so it detects if queries, and when a Elasticsearch query comes in, there's a DSL to this. So if the DSL if the query has a full text query in it, we have ways to figure that out. So if there is a full text query in it, it forwards that query onto the ML search service, which then comes back with the document IDs that should be included, and then a query is reconstructed and forwarded down to Elasticsearch, which then returns the actual results. So to a user, it doesn't seem like anything's changed. The interface is still the same, yet the results are better. Well, actually, I didn't mean to end it that abruptly, but yeah, that's it. Any questions?
So in the paragraphic vector model, so for each paragraph, do you actually represent that as the company name plus the description on the company? So how do you generate the paragraph?
Right. Good question. Oh, I can just use this one, right? Good question. So what we actually did, the paragraph vector model itself was trained unsupervisedly on lots of news articles that we have. So like that is domain specific information, right? Like we have news articles about businesses, like 4 million something news articles. So we trained the paragraph vector model on that. And then, so the model is trained, we pass in to encode into a single vector a concatenated version of all the text that we have about a company. So like it's description on Twitter, it's description on other things, and then it's about page text, it's landing page text. So taking all of that text together, we passed it into the model, which gives us a vector for the company.
So do you create a vector for each individual terms in the query and aggregate it together and then use it for matching? Or do you create one single vector for using paragraph to vec and then do the matching?
Yeah, good question. So no, we create one vector in the same way that you would put in a large document into the paragraph vector model. We put in the short query phrase. We did test what would it be like if we just like we just summed up the vectors or averaged out the vectors of each term. Turns out that's much worse, and it kind of makes sense because it loses the meaning of order that paragraph vectors can have for you because it uses windows. So the way paragraph vectors encode a vector is windowing through, whereas if you just use the word vectors, you would lose that. So like sharing economy would be the same as economy sharing, whereas in paragraph vectors it wouldn't.
Is it similar to like in Spark?
You can actually compute the vectors using word to vec and aggregate it across all the document, right? How does that approach compare to what you're doing using paragraph to vec?
So I think in economy sharing, sharing economy and economy sharing, Spark would do the same thing in this aggregation because it would just be summing the vectors. So addition is transitive. Is it transitive? Anyway, it would be the same on both directions, right?
I was wondering what paragraph vectors implementation you used, and if there were any tips as far as the parameters, dimensionality, modes that turned out to be most useful.
Cool. I'm assuming you're familiar with Gensim. Yes, cool. Otherwise, that question is a little hard to answer because we use Gensim. Great library, by the way, for text analysis. Probably the best word-to-vec library also. Anyway, what we found out is that we tried a whole bunch of parameter optimizations, actually across all of our models that we tried, the LSTM, the RNN, the CNN. We tried to optimize all of the hyperparameters, right? It's not like we took shortcuts because we were like, oh, we have a favoritism towards one of these models. I actually didn't know which one would be better. But so for those who know paragraph vectors, you could do it in two different ways. You could do distributed bag of words, or you could do DMM. I forget exactly what the acronym is, but one of the DBOW works better for comparing short phrases to large documents than DMM does. But we found that out when we did all this hyperparameter tuning. So it turns out that if you definitely want shorter windows, not too short, something around 5 if you're doing this kind of textual search, and you want to use DBOW.
what about the dimensions, right? Typically, it's said if you use Sparklet, it's more than anything more than 300 is better.
Yep.
But it has an infrastructure limitation, the memory aspects, etc. What have you used successfully?
So we tried 3 different things. We tried 100, 200, and 300. With 300, we were also able to do something where we were able to initialize the word vectors with pre-computed word vectors. So in training a doc-to-vec model, you're using a word-to-vec model really in the bottom. But what you can do is you can initialize the word vectors with kind of general purpose word vectors, even though you're training on a domain. So what we did was we used the glove implementation word vectors, the general glove trained on Common Crawl. So you could do that on the 300-dimensional word vectors because they put out 300-dimensional vectors, but they don't have 100 or 200-dimensional vectors. So we did the hyperparameter tuning. That was part of the hyperparameter tuning, the dimensionality, but we ended up with 300 dimensions with the intersection with the glove vectors, and that worked really well.
More questions? Okay, then thank you so much. Samiur Rahman, Mattermark. Thank you.
Thanks, guys. Since I have a little bit more time, I'm going to make a PSA and say, not a PSA, but an advertisement more. We're hiring machine learning engineers at Mattermark. If you want to, if you're interested, email me. We're working on some really awesome stuff. At least I think so. Cool. Cool. Thanks, guys.